Hey everybody, in this video we're going to talk a little bit about the superposition of electric fields. Let's start by asking the obvious question, what is superposition? In this context, superposition is sort of just a fancy word for adding up. Suppose that we had two objects that were both producing electric fields, and we brought them close enough that their electric fields overlapped. This overlapping is known as superposition. The two fields are both affecting the same regions. So we have to figure out how these electric fields add up when they're together. To do that, let's start by considering an example that you saw in DL today. We have here a positive charge and a negative charge separated by some distance. We want to know what the overall electric field looks like when we take both of these charges into account. I claim we've already learned everything that we need to know about how to do this. Let's pick a point on this graph and try to figure out what the overall electric field looks like at that particular point. The easiest way to do this is to start by drawing what the individual electric fields look like at this point. We'll start by pretending that the positive charge is the only charge that exists. What does the electric field here look like if we're only considering the positive charge? We know that an electric field always points away from a positive charge. So the electric field at this point for this positive charge looks something like this. The electric field is pointing directly away from this positive charge. Now let's do the same thing, but for the negative charge. What does the electric field from a negative charge look like? Well, we know that it's the exact opposite of a positive charge. The electric field always points towards the negative charge. So the electric field here from the negative charge points towards the negative charge. But how large is it? Let's assume that these charges are the same. Which charge is this point closer to, the positive charge or the negative charge? Well, it looks to me like this point is closer to the positive charge. So we expect the electric field from the positive charge to be stronger here than the electric field from the negative charge. A stronger electric field means a longer arrow. So we expect this black arrow to be larger than the purple arrow we're about to draw. So we expect that the electric field from this charge looks something like this. So what does the overall electric field look like? Well, because these are two vectors, they can just be added up. If you don't remember how this works, I'll leave a link in the description to the video we did a few DLs ago about this. We add up vectors by just placing them tip to tail, and then drawing a vector from the beginning to the end. Let's do that here. Let's move this purple vector from here to here and see what the overall vector is. So the overall electric field at this point points in this direction. Let's pick another point and see if we can do the same thing. Let's pick right here. What does the overall electric field look like at this point? To do that, we just do the same process that we did for this point. We find out what the electric field would be from the individual charges and then add them up. What will the electric field from the positive charge look like at this point? Well, as before, the electric field from the positive charge will point away from that charge, and the electric field from the negative charge will point towards that charge. But this time, the positive charge is farther away than the negative charge. So we expect the length of the arrow for the positive electric field to be shorter than the length of the arrow for the negative electric field. And now, just as before, we just add up these two vectors in order to find the overall electric field at that point. When I add these vectors up, I get something that looks roughly like that. Notice an interesting feature about these electric fields. The individual electric fields produced by the positive and negative charges always point directly towards or directly away from those charges. But when we add the two together, we don't get something that points towards or away from one of these two charges. It points off in other directions. This is just how electric fields work. Imagine that you place a positive charge right here. As we know, it will be repelled by this positive charge because like charges repel. But it's also being attracted by this negative charge at the same time because opposite charges attract. And so the overall effect is some weird force that points off in this direction. Let's do one more example with a slightly more complicated arrangement of charges. Let's imagine that we have this little triangle of charge. Let's ask ourselves what the electric field is at the very center of this triangle, right about here. We'll proceed the exact same way that we did before. Let's start by asking what the electric field looks like from just the positive particle. As before, we know that this electric field points directly away from this positive particle. What about the electric field from this negative particle? Well, we know that the electric field around a negative particle just points straight towards that negative particle. And lastly, we'll do this negative particle. It's the same thing as with the first negative particle. The electric field from this particle just points towards it. So now we have our three individual electric fields, one from this positive charge and one from each of these negative charges. But we want to know the overall electric field that gets created when we put all these particles together. We can add three vectors the same way that we added two vectors. We just place them tip to tail as many times as we need to. If we do that with these three vectors, we get an electric field that looks like this. And there's our answer. At the center of this configuration of charges, the electric field points straight down. Let's do the same exercise by thinking about forces. Let's imagine that we placed a positive charge at this point. What would each of the individual charges be doing? Well, the positive charge up here is just going to repel the new positive charge, pushing it straight down. The negative charge here will pull that charge this way towards itself, and this other negative charge will pull that charge this way towards itself. But notice that one of these negative charges will be pulling the new charge to the right, and one of them will be pulling the new charge to the left. These individual pieces will cancel each other out. It's like the two negative charges are having a tug of war, but they're completely evenly matched. Neither of them wins. So the only piece of the overall force that is left over is the force that points straight down. And so the positive charge here will feel a force in this direction. So let's write down a recipe for finding the electric field for multiple charges. First, we pick a point that we're interested in. Second, we go charge by charge and figure out what the electric field will look like at this point, considering only one of the charges. Once we've found what the electric field looks like for each of the individual charges, we just use vector addition to add them all up. Once we've done that, we can just pick a new point and repeat this process as many times as we need to get a good outline of what the electric field looks like. As I said, all of these things are things that we've done before. We can pick a point just fine. We know how to figure out what the electric field looks like for a single charge at any point. And we also know how to add vectors together. If you follow along with this recipe, you should always be able to draw what the superposition of two electric fields looks like. It might take a little practice to get it exactly right, but I'm confident that you can get it. Next DL, we're going to look a little more closely at one of the examples we just did. The example is when we have two nearby charges, one of which is positive and one of which is negative. This is known as a dipole, and it turns out to be interesting enough to study on its own. But we're also going to introduce a new idea that you're undoubtedly familiar with, but perhaps not in a precise way. It's electricity's dark twin, magnetism.